Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as Interference of Light. Let's see the sum please. What is the minimum distance? What is the minimum distance between 2 points that will permit them? What is the minimum distance between 2 points that will permit them to be resolved, at 2 kilometers, that will permit them to be resolved at 2 kilometers using a terrestrial telescope of 6.5 into 10 raised to minus 2 meter diameter using an object 6.5 into 10 raised to minus 2 meter diameter and a wavelength of 5,500 Armstrong unit Now let's assume that the 2 points are A and B, right? Let's assume that the distance between A and B is x. So you would say let us assume let x be the separation. Let x be the separation between the 2 points A and B, right? X is the separation between the 2 points A and B. Now, let us assume that d theta is the angle subtended by them at the objective. Let d theta be the angle subtended at the objective, right? In which case we know that d theta is given by the formula 1.22 lambda for a telescope, 1.22 lambda upon d, right? Now we also know that s is equal to r theta. Length of the arc is radius into theta. Now in that case, for this given figure, length of the arc is x, right? R theta, radius is nothing but d and theta is d theta. For this particular triangle, guys, please see this triangle. This is going to be my length of the arc, this is the radius and this is the angle subtended at the center. So in that case, I can therefore say that d theta is x upon d, right? Do we get this in here? Now, substitute this, so I can say, but we had already said that d theta is 1.22 lambda upon d. Therefore, I can say x upon d is 1.22 lambda upon d. They have asked you to find out the value of x. So, I can say that therefore, x is going to be 1.22 lambda into d upon d. You have all the values, you know the value of d is 2 kilometers, and see this can be written as 1.22 lambda 5,500 into 10 raised to minus 10, d is 2 kilometers, so 2 into 10 raised to 3 meters upon small d is 6.5 into 10 raised to minus 2, right? So when you solve this, you will come to know what is the minimum separation between the 2 points. You will get this answer as 2.065 centimeters. Fine. See now next one please. A telescope with a vertical slit. Of 2 millimeter. A telescope with a vertical slit of 2 millimeters in front of it is used to observe the headlights of a car which are 1.2 meters apart. Is used to observe the headlights of a car which are 1.2 meter apart. The diameter of the objective is 2 centimeters. The diameter of the objective is 2 centimeters and the light used is of 5000 Armstrong units. Find the distance of the car when the images of the headlights are just resolved what should be the distance of the car? Next part of the question. What should be the distance of the car for the images to be resolved when the slit is removed? Right? Now let us assume that these are the two headlights of the car which have to be resolved by the using a telescope. Now instead of directly seeing the headlights, what have we done? We put a slit in front of them. Right? The slit is a let's call the slit as say CD. We've already used AB as the headlights of the car. Right? So we've used a slit in front of this. The light which is being used is of 5000 Armstrong units. Right? Now they are asking you what should be the distance of the car. Let's call this. Let's assume that capital D is the distance at which the car should be so that the two images are resolved. Now I have to do this experiment twice. Once with the slit in front of it, once without the slit. Okay? Now, I can say in the presence of the slit, I can say that A times sine theta is n lambda. Right? Do we get this thing here? So in that case, I can say that since theta is very small, I can say A theta n is going to be 1 because I am looking at the central band. So n is going to be 1. So I'll get A theta is equal to 1 into lambda. That is, I can say A theta is equal to lambda. Since sin theta is very small, sin theta can be assumed as theta. So in that case, I can say that theta is equal to lambda upon A. I can therefore say that theta is lambda upon A. Once I have this, but I can say that theta is equal to x upon d. Theta is also equal to x upon, right? But theta is also equal to x upon d. Therefore, I can say that lambda upon A is equal to x upon d. Therefore, I can say d is equal to ax upon lambda. So I'll come to know, I know the slit, I know x, I know lambda. So I can find out the distance of the car. I should be able to solve this. Next, in the absence of slit, now in the absence of slit, I can directly use the formula for telescope, that is d theta is 1.22 lambda upon d. I know lambda, I know d. I should be able to get this, and I can also say that d theta is also equal to x upon d. Therefore, I can say x upon d is 1.22 lambda upon d. Therefore, d is xd upon 1.22 lambda. So I'll come to know the distance of the car when the slit is removed. So we can find out the distance of the car with the slit and without the slit. The answer for this sum should be with the slit, the first part is going to be 4.8 kilometers, and second part without the slit is 39.3 kilometers. Right? Next, take on next one please. What should be the minimum distance between 2 points that will permit them to be resolved, at a distance of 1 kilometer using first part of the question, a terrestrial telescope using first part of the question, a terrestrial telescope of 6.5 centimeters, a terrestrial telescope of 6.5 centimeters diameter and 6.5 centimeter diameter and 550 nanometer and 550 nanometer wavelength. Second part of the question, using an unaided eye, with a pupil diameter of 2.5 millimeter. Using an unaided eye of pupil diameter 2.5 millimeter. Guys, let's try to understand this. They're saying what is the minimum distance between 2 points that will permit them to be resolved. Let's assume A and B are the 2 points, right? The distance between them is x. What is the minimum distance between 2 points that will permit them to be resolved at 1 kilometer? This distance is 1 kilometer. Here's the telescope. Okay. This angle is theta, d theta. Let's call this angle as d theta. Right? Now, I can say for let x be the separation between the 2 points. In which case I can say that for a telescope, I can say that d theta is 1.22 lambda upon d, right? But we know that s is equal to r theta. We've done this in a previous sum also. S, the length of the arc is x, right? Radius is d, and theta is d theta. Therefore, I can say d theta is x upon d, right? So, and d theta we said is 1.22 lambda upon d. So, I can say 1.22 lambda upon d is x upon d. So I can get the value of x from here. I can therefore say that x is 1.22 lambda d upon d. So you will come to know the minimum distance at which an object, what should be the minimum distance between the 2 points so that they can be resolved at a distance of 1 kilometer. Second, now instead of the telescope, you are using your eye. Now your eye, the pupil of the eye you are using, whose diameter is 2.5 millimeter. You will use the same thing, I can say, for the unaided eye. The unaided eye also, the pupil of the unaided eye works like the objective of the telescope. Therefore, I can say that again here d theta is going to be 1.22 lambda upon d1. I have taken the objective to be d1. Same thing I can say that now. I could say that d theta is also equal to x1 upon d. Therefore, I can say that 1.22 lambda upon d1 is x1 upon d. Therefore, I can say x1 is 1.22 lambda d upon d1. So that should be the minimum, x1 should be the minimum distance at which the two objects should be, so that they can be easily resolved by the unaided eye. Okay, the answer for this sum should be x is going to be 1.032 centimeters and x1 should be 26.84 centimeters. Next, take the next one please. In an experiment with the microscope, light of wavelength 5800 Armstrong units is used. The semi-vertical angle is 45 degree. Calculate the limit of resolution. Calculate the limit of resolution and the resolving power. Calculate the limit of resolution and the resolving power. Now I can say for a microscope, dx, the minimum distance at which the 2 points is given by the formula lambda upon 2n sin theta, right? Since experiment in air, therefore the refractive index will be 1. Therefore, I will get dx is lambda upon 2 sin theta. I know the value of lambda, I know the value of theta. I can substitute and get the answer for dx. Once I know this, this is my limit of resolution. So my limit of resolution will be dx, and they ask you resolving power. Resolving power is given by the formula 1 by dx. You already have found out the value of dx, reciprocate it, you should get that answer. The answer for this sum should be dx is going to be equal to 4.102 into 10 raised to minus 7 meters, and the resolving power is going to be 2.438 into 10 raised to 6. Right, take our next up please. The limit of resolution of a simple microscope, is 2.4 into 10 raised to minus 7 meters. If the semi-vertical angle is 50 degrees, calculate the wavelength of light used. Calculate the wavelength of light used. Calculate the wavelength of light used. Straightforward sum, I can say that for a microscope, dx is equal to lambda upon 2n sin theta, where I can say n is equal to 1 because the experiment is being done in air. Dx I know, theta I know, lambda is the only unknown. So I can say lambda is equal to dx into 2 sin theta. N is 1. So substitute and you should get the answer. The answer for this sum should be 3677 Armstrong units. Next, take our next sum please. In an oil immersion microscope, in an oil immersion microscope of refractive index, in an oil immersion microscope of refractive index 1.412, the wavelength of light is 4850 Armstrong units. The wavelength of light is 4850 Armstrong units, and the semi-vertical angle is 45 degrees. Calculate the limit of resolution and the resolving power. Calculate the limit of resolution and the resolving power. Calculate the limit of resolution and the resolving power. Limit of resolution for a simple microscope dx is given by the formula lambda upon 2n sin theta, n lambda theta. All three values I know. I should be able to get this value of dx, and resolving power is the reciprocal of limit of resolution. So resolving power is nothing but 1 upon dx. Again I know dx, I should get the answer. The answer for this sum should be dx should come out to be 2.43 into 10 raised to minus 7 meters, and the resolving power should be 4.115 into 10 raised to 6 meters. 10 raised to 6. Right? Next, last sum to finish the chapter. Find the angular and the linear separation. Find the angular and the linear separation between 2 points on the earth which an astronaut 160 kilometers away, which an astronaut 160 kilometers away from the earth can see, 160 kilometers away from the earth can see just resolved. 160 kilometers away from the earth can see just resolved. If the wavelength is 540 nanometers, if the wavelength is 540 nanometers and the diameter of the pupil is 2 millimeters. Now for a telescope, your eye is going to be acting as a telescope, so the angular separation d theta is nothing but 1.22 lambda upon d, right? I know d, I know lambda, I think that what will be the angular separation. I'll get the answer in terms of radians. I'll get this answer as 0.33 into 10 raised to minus 3 radians. That should be the angular separation. Now let's assume that if x, let the linear separation let us assume that the linear separation is say x, then I can say that d theta is nothing but x upon d. Therefore I can say x is equal to d theta, d into d theta. D I know, d theta I just found out, so I should be able to get the linear separation. The answer for this should come to 52.7 meters. So the linear separation between the 2 points should be 52.7 meters. This finishes this chapter. We'll stop this here for the day. Thank you very much.